So go to this page here in GitHub, and now you have a few options to use the notebooks. You can clone or download the notebooks depending on you prefer to use zip files or using Git. If you don't have iJulia working, that's not too bad because, oh, I'm master already. You can just open the notebook here. And then this will show the notebook that we're using as it was in iJulia. So you can follow through the steps here. And if your iJulia doesn't work, you can just open the Julia terminal and copy the lines of code to the black screen. Well,
checkout, to do the checkout, do I do it inside Julia or just get from
yes. Yeah, this is, the notebooks are not a Julia package with notebooks. It's just a Git repo. So if you're using iJulia, you should do using iJulia and then notebook. So it will start an iJulia instance. So these notebooks, most of them have been up for a while, and we just updated them for the latest version of Julia Master. Now we have a little bit to wait a little bit for Julia. Okay. Mine is here, notebooks. So I will start with this getting started with JuMP. And there's also okay. So yeah, this notebook was written by Benoit a long time ago, but now it's updated to this new version.
So which one did you click?
So I clicked in Benoit - getting started with JuMP. I think it should be the last one. So it starts with introducing Julia, saying a little bit about what is JuMP, why do we want to use JuMP, because, well, it's everybody, most of the people here have at least heard from somebody that is a pretty awesome way to write your mathematical programs and solve them. It's solver independent, it's easy to write programs. It interacts perfectly well with Julia since it's a package in Julia. Well, and so there's some extra stuff telling you how to install Julia and iJulia, and then it tells us how to install JuMP. So in order to install JuMP, we did what we have done. You have to package add JuMP, and to use the latest version that we're using right now, you have to actually go through an extra step, which is the package checkout JuMP, because we're not using a stable version. Well, it's stable, but it's a beta version. So the second thing you should do when you're using JuMP, you should use a solver. So most of the time you want to build a model and solve it. Although you can just build a model if you're happy with that, and then do whatever you do with a unsolvable model. So the main solver, well, in the latest, using MathProgBase, which is something that works on JuMP 18, and it's not working with JuMP 0.19. There were like maybe more than 20 solvers that are working perfectly fine. And now we are replacing this intermediate layer between JuMP and the solvers, which was called MathProgBase, and the new one is MathOptInterface, which is in the list there of packages we should have. And so we have updated many interfaces, and there are a few of them working right now. We'll be using today GLPK, IPOpt, and I think CSDP. These are tagged and should be working fine. Express, Gurobi, and Cplex should be working soon. I think Gurobi and Express next week. CLP and CBC soon also. Maybe in 1 or 2 weeks or a little more. Mosaic is working also with this new framework, but I don't have Mosaic here in my computer.
SQP works.
Oh, SQP works, perfect. I haven't tried to download. That's the only reason I'm not using that. Because all my Julia was stable. I was like, I will not add another package because who knows what package update will break if I do that. Okay, so you can, in order just to test if your notebook is working fine, you can, well, just run this line, and it's an asterisk when it's running, and when it stops running, it writes a number over there, writes the output, and here's where we start. So for this notebook, the packages, well, first you add the packages so you have them in your repo, and then you have to say you're using those packages. So you have to include all the data from those packages, all the functions in your workspace or your environment. So you run this second cell here, which is using JuMP, using MathOptInterface, and using GLPK. I did this const thing because sometimes I want to use some functions that belong to one of these packages, MathOptInterface or MathOptInterface utilities. But instead of writing everything, I would just write those shorthands for this. So
Jared, you have no excuse anymore for not knowing Jump.
I don't know optimization.
I had a slide there. It has to learn optimization using Jump.
So here is maybe one of the simplest optimization problems you could write. Well, the notebook is nice because, well, you can click in this cell. It's written in LaTeX, so it's good for documenting and showing these live demos, as long as iJulia works. So we're minimizing the sum of x plus y, subject to x plus y is smaller than 1, x is positive, y is positive, and those both are real numbers. So the solution is pretty straightforward. It will be 0 for x and y. Not very creative, but let's start with that.
Is the GLPK dot, so is that convention now doing GLPK dot?
So we haven't fixed the standard for the how do you use a solver. So here in this first line of the code, we will write this model and then solve it. So the first step is that you create an empty model with this function model, and you could use model with no arguments, and then you wouldn't have a solver, and that's what I was talking about of having a model without a solver. You can also attach a solver later, but let's leave it that for later. But the standard way to use JuMP is to use this keyword optimizer, and then you say which solver or optimizer. These words will be used interchangeably. Solver would be the word we used for MathProgBase, and now in MOI, MathOptInterface, we're using the word optimizer, so then we don't have a crash of names. Well, GLPK dot is because this function, which initializes the solver object, is not exported. So you have to use the GLPK dot in the beginning, but I don't think we have a standard for that. We're planning to export, or yes, because yes, we could not export and not write GLPK here or do something like that. But well, there's something else that's different from in GLPK between the other solvers, that GLPK has two solvers inside of it. It has a linear solver and a mixed integer programming solver. So it exports two different objects. So in the beginning of the presentation, I'm using the linear programming solver, which is GLPK Optimizer LP. Okay, so once you have started with a model object, we have to start building our optimization program in it. So the first thing you need is probably the variables, because, well, you need them to write the objective function and the constraints. So you start with these variables macros, which is just like a function in which you say, so I will add a variable to my model, and this variable is named x, and it's greater or equal than 0. And then I'm adding another variable to my model, and this variable is named y, and it's greater or equal to 0 again. Well, the second thing you can do is add constraints or objective. There's no need for an order to do that. You can do in any order now. Well, even you can add a variable after a constraint if that constraint doesn't use that variable. So you can do in any order you prefer, as long as the variables you're using are already defined. So now we are defining objective. Objective have one extra parameter, so we're creating an objective to my model, and this will be a minimization objective, and we are minimizing x plus y. We could also use max for maximization. Okay, and then we add our constraint, which is just x plus y smaller or equal to 1 to my model. What's the second step after you add your whole model? You want to solve it. So we're using this function, JuMP-optimize, and you say, oh, I'm optimizing my model, and then it's done. After you optimize your model, you have to go through and see, well, you don't need, but you should see if, well, first of all, if your model has results, your model has a termination status, and which status is that? Because it could be success or some other fail statuses. I will talk about that in a second. And you could query about other information like primal status. So is your solution from your problem feasible? Is it unfeasible? Is it something else? And then you can query results from your model. So you can query the objective value with this JuMP.objectiveValue function, and you can query results from your variables. This will query primal results from them. So JuMP.resultValue x will query the result for x, and the same thing for y. So you can just run this cell. So it has a asterisk over here. When your notebook has this colored ball, it's running. When it's not, then it's run already. And then it printed these solutions, which are, well, the objective value, the value for x, and the value for I. I also showed what's happening in the first 3 functions. So the first function is saying, well, I have result values. The second one is saying, well, my status is actually equal to MOI success, which means, well, we have a solution and we can do something with that. And primal status is a feasible point, which makes sense because our model, this was a feasible and actually optimal solution for that model. A little bit about statuses. Well, Miles talked a little bit about this, yesterday. So once you solve a model, you have a few options about what's going to happen. So suppose you're solving a problem with a primal dual solver. This is a slide from Miles' presentation. Then you have a termination status, which could be success, almost success, slow progress, or other statuses. So success means it gets some result. At least the solver says, well, I finished, I have some information for you. It should be an optimal solution, or typically an infeasibility certificate. So the solver was successful on doing everything it could for this problem. It either found an optimal feasible solution or an infeasibility certificate. Well, if you have, sometimes the solvers have relaxed tolerances, so you have other statuses like almost success, and sometimes the solver cannot solve the model, like a huge model, there's not enough time in the limit, or enough some other user function that you use to stop the model, so it returns this slow progress, which means, well, I tried for a long time, but I couldn't finish with that. There's this other function I haven't used, which is a result count. You could query how many results, but currently all the solvers are saying they either have one result or they have none. But it's possible that soon we have a solver that says, well, I have two solutions for you. And then we have the primal status and the dual status. The primal status could be a feasible point. The dual status can also be a feasible point, or both could be infeasible if the solver finds an infeasible solution and stops with one of those. Or it could be an infeasibility certificate like a dual ray or a primal ray, showing the infeasibility direction or unboundedness direction. Then it would be either a dual infeasibility certificate or a primal infeasibility certificate. And then, well, you could have also almost feasible points, which just mean they are feasible within some relaxed tolerances other than the default tolerances or the tolerances you set to use for this problem. Well, more options that you could also have is that when you're using a MIP solver, you could have other statuses, like, for instance, if the problem is solved and it's said to be infeasible or unbounded, it could be also infeasible and there's no result to show. Some time limit might be reached. And then, well, in all these cases, you could have a result count. So if you found an optimal solution, it will say, well, I have one result, it's a feasible point. Well, it's a MIP, so it probably doesn't have a dual variable that makes sense for this solution. Currently, the other options raise errors. So if you have an infeasible problem, then, well, you shouldn't query for primal status and dual status. The same for, well, in MIP for unbounded or no results. Well, sometimes you can have a certificate for unbounded MIPs because you'd just be like the first node relaxation is unbounded. And then there are some weird statuses from some solvers, like CPX optimal infeas, which is like something weird, which is a success because it did everything it could, and it spits a infeasible point. So there are many statuses. I encourage people to look at the MOI manual later to see more details on those statuses. We can talk more about them later. So okay. So after we solve this very first version of a problem, a little bit of Julia so that we can have like a little bit more complex models. So if you want to write a column vector, you just do the numbers separate by semicolons and between square brackets. If you want to do a row vector, you don't separate them by semicolons. You can also build a matrix, like this A matrix. You could use this thing to build a matrix. So if you run this cell over here. Well, wait. I opened the wrong one. The not running one. So you can run that, and then A is a matrix in your problem, in your program currently. We haven't started to build another problem. Some useful functions are, well, this print ln function, it just prints a line, it prints a string, and then adds a line ending command after that. You can use strings in between and numbers in between that, so that it will print the numbers or the vectors which are between the strings. Some other operation that is useful is the dot product. So if you have two vectors, you can find a dot product between them using that function. So what else? Okay, so after I show the first example, we're going through in a little detail about all the little pieces in JuMP. Okay, so you might say that JuMP has like 5 main objects. The first one is the model, which handles all the other objects. The second one is an optimizer object, which you can plug to the model to use that to solve a program. You can have variables on your model, constraints, and objective function. So, well, in the model, as we've seen before, we can initialize it by using this model in model function, and that will initialize a model without a optimizer or a solver. If you're doing, well, then you have, well, the possible solvers you could use. This is just a non-exhaustive list. There are linear programming solvers like CLP optimizer and GLPK optimizer, LP. We have mixed integer solvers, and then there is also commercial solvers like Express, Gurobi, and Cplex. There are conic solvers like SCS. There are SDP solvers like SDP. There are Mosaic. There are many others that work with JuMP. Any question?
We can sue open sources?
Why?
No, it's a funny typo.
Oh, okay. Oh, yes. You shouldn't sue an open source solver. You shouldn't do that. We have to use them. Then there's something that Miles talked about yesterday. I will leave that for later. Is that now JuMP has many modes for working. You could have like this mode word, so you can use JuMP in automatic mode, in manual mode, and direct mode. I will be back for that later. But the thing is, for now and for most people, all you need to know is that, well, you can initialize a model with an optimizer, and that will be all that you need for most of your problems. If you're doing callbacks or lots of modifications on your problem, you might go through the other options. We will talk about that after more examples. So here, well, where? Somebody said something? No. Where is it? What? Okay. So more details on variables. If you want to create a variable, you can, well, first you need a model if you want to create a variable, and then you use a variable macro. We have already used the variable macro defining a lower bound for the variable, but you could also initialize a variable with both bounds or none of its bounds. Something else you can do is you can, well, all we did so far is initialize scalar variables. But you can also have vector variables and much more complex variables with different structures. So the first one is a vector variable. I will define a vector variable with 10 variables with these lower bounds and these upper bounds defined by these two vectors. So we have a syntax for that, which is pretty straightforward. You're still adding a variable to my model, but now this variable still has a lower bound and has an upper bound, but the upper bound and the lower bound depend on the index of the variable. So here the variable will have indexes I in 1 to n, and these are the indices you're going to use from those vectors up there. Okay? Well, there are other kinds of variables, because so far we only did continuous variables. You can also have binary variables, integer variables, and some other weird kind of variables like semi-continuous or semi-integer, but I think they come like this?
MPSD.
Okay. Oh, yeah, and there's also positive definite variables for matrices. Well, sometimes, well, it's a very common situation to define a variable, a range of variables, and all of them are positive. So you don't need to have an explicit bound for each of those. You could just say, okay, let's create a vector with 4 variables and define it over there, and all of them are positive.
Can I do 0 less than or equal than?
What?
Can I do 0 less than or equal than xx I 1 to n?
No, yeah, it has to be on the other side, always. So if you do y, then you should ask Miles.
Just Benoit.
Okay, Benoit.
Why can you flip?
Yeah.
You can.
When in the micro you cannot know if you do x larger than a.
When zero is there, you know.
Yeah, we can. But if we allow that, I mean, it works if you put 0 because we see that it's 0. But if you put a equals 0 above and then you put a, we only see a, we do not see 0, and then it won't work.
I don't know which one of those are, the variable or the constant.
Yeah. So the constant work, but not if there is if it's a variable that's defined. And so what we do is when there is a constant, then we can throw a very helpful error so that people understand that this is not allowed. And when there is not a constant,
Let's do it.
the variable that is defined above, then we throw a very unhelpful error. But at least they warn what they do is constant.
So if we did like this, and it says, okay, S is not defined, but S is a set. It's a bad error, but
Why?
but you what?
Why did it throw that?
Why did it throw this error? I have no idea.
Try with the.
You want to float?
Maybe not an array, just x. Yeah.
Oh, my bad. S is not defined. So we have work for Benoit for later.
Is there a way to get it to be more more explanatory error?
Yeah, it should
Yeah,
be.
there should be a very nice error. But apparently there's.
Even with A, because like, this is like I've gotten a lot of complaints. So it's like, why?
Yeah, for a long time it was not a good error, but it was a recent fix that it turned to be a good error, but apparently not anymore. Well, but then you can also do other things like define an integer variable. So you define a variable with its bounds. Well, it might not need a bounds. It could be an unbounded integer variable, but still you add that int keyword just to say this variable will be integer in your program. And you could do the same thing for binary variables. So, yes, please.
To summarize, you can do 0 less or equal than x less or equal than
Something else. You
that
can do
works.
that. Yeah.
0 less or equal than x. That doesn't work.
Only on the, well, if you only have one side, this bound has to be on the right side.
Okay, perfect.
It could be less than equal or greater than equal, but it has to be on the right side. That's a technical problem because the macro reads the string that is inside the parentheses, and it tries to figure out what's your variable they're creating and what's the data for the bound. So that's why.
Thanks.
Okay, once you have your variables, you can start building constraints. So for that, we use the constraint macro, which is a very useful way to write constraints. You start again writing a model, and then, well, you need variables on your constraint, and so you create a variable, add to the model, and then you create a constraint just like we did before. Okay? Something that is very useful quite frequently is you want to have references to your constraints because, okay, if you only care about primal results, you add your variables, add your constraints, solve your model, and then query the primal results, which means the variable solutions. But you could also ask for dual variables, which are usually associated with constraints. You could ask for a variable dual, which would be typically a result reduced cost of the variable. But if you want the duals for constraints, you have to ask like, well, I want the dual for this constraint. So you need to have a name for that and a variable on your system for that. So every time you use the constraint macro, it returns a constraint reference, which it doesn't seem to be very simple, but it's actually very simple and you don't have to care about what is inside of it. So this is the underlying structure, but that's not important if you're only using JuMP. Then you can have a constraint reference. Another way to create the constraint reference is you can add a constraint to your model, and then you say the name of the constraint reference, you want to save it, and then write your constraint. So it also returns the constraint reference, so it will save the constraint reference to something you're returning, and this is just showing that both are the same reference. You don't, yeah, please, Francois.
What if this reference already exists in the world?
So yeah, let me show you that. Let's go up here, create a model, add variables, and then you add constraint number 1, and now you want to add again constraint number 1. It shouldn't work. Oh, so what happened here? Here I added this constraint and I picked the reference, this function spit it out, and put it in this variable, okay? So this constraint won't have a name inside your model because you haven't said that. You're just holding the reference in this variable. So if you run this function as many times as you want, it will not complain, but well, you can see that this number here is changing. So it's creating different variables and each of them is replacing the last one in this reference. But your model still stores all the references. But if you write this way, then your model will be aware of the name you gave to the constraint. Okay? So if you run this thing twice, first time, and then second time, it will say, well, constraint name conref2 already is used. So you have to use a different name. like then you can create another one. That's because your model has to if it knows about, it has two options. Either it doesn't care about the name of the constraint. This is what we call anonymous constraint. Or if it has a name, it has to be unique. In the past, we allowed people to add multiple constraints with the same name, but that was a big mess because sometimes people wanted to get back the first one, but that doesn't make sense anymore.
So if I do the your model bracket colon conref,
Yes?
I will get back the reference to conref.
Yes, so view. I never know how to add a cell without this. So, well, first of all, conref creates automatically a variable on the workspace. So here is the same reference. And the second thing is what Juan Pablo was saying. Does it work? I don't remember. It should. Ref.
Works for me. It did something.
Okay, so
It looks like the same.
yeah. What happened now is that, well, you save this reference in this local variable, but then you can say, well, conref equals 4. So, So what happened here? I created a constraint tied to this reference. So your model is aware of that name. And it also creates this variable on your workspace so you can have the reference for yourself. Then I said, okay, conref now equals 4. So this variable lost the reference. So if I just go and do conref, it will just be 4. I lost the reference, but I could get that back by using this function here. So you query your model for this index inside the model, which is the name of the constraint reference.
What
So
about your model? Okay.
you do that, and then
You put the other piece.
yeah. So it used to be a number 7 here. Let me show you. Let's do conref 5 and then xx qq equals conref 5 and then conref 5 equals 5. Okay, so I lost the reference, but I'm keeping this variable here. So that's the reference. And then I can query the model for the name of the reference. And those are exactly the same. So
I'm confused because you use name and index
yes.
one for another. So what is the idea of the construct? Is it an index or is it a name? A string?
Do your model conref 1.
You want to do
No,
this?
the 29? In 29?
Okay.
Put conref 1.
In the syntax there.
No, it doesn't. It started with 2.
So, but you actually, you have conref 1. So if you look at the syntax in 17, you're getting conref 1 equal, and that's a variable. Think about it as a pointer to the constraint.
It's both a pointer and an integer that represents the syntax?
No, it's a pointer.
So yeah, it's always a pointer.
But it's a subset like when you declare the conref 5 in 27, the pointer is now saved in the model, and you can recover it calling
Yes.
your model colon conref 5.
All right.
So if you rewrite your pointer
as an index, integer index, or is a name, a string name, is really a pointer.
It's really a pointer, yeah. There's also the feature for a string name.
Yeah.
So,
But so then your model dot colon conref, so it's like a dictionary that returns the pointer.
yes.
So if you lost the pointer, you can recover it with a symbol. If you declared it inside the add constraint, your model colon conref. If you did it the first time, the only thing you did, you got the pointer and you saved it in the variable conref1, and if you override it, you lost it.
Yeah, and that's very useful when you build a model inside a function, and then all your pointers are in your scope. Then you leave the function, and you want to query results in another function, and then you can query back the names of the constraints and variables from this other scope.
Or if you call it, let's say, with your model, and you create a new your model, you have your model bracket 1 to n, and you're repeating these over and over again. So conref5 is going to be rewritten every time the conref, the variable outside. But the model, your model 1 colon conref, will always be the one for that particular model. So then it's fine if you overwrite it. Again, now these variables are going to be temporary. Every time you use it, you rewrite it, you can always recover the correct one going to. Now, I guess you cannot really do it in the 17 because that conref equal, there's no way for the model to know that you wanted to save the pointer. But on the second and
Yes.
27, it knows, oh, conref, great, I know how you're going to call it, save.
So you have a global memory of the...
Yes.
Or it's internal.
Yeah.
To the model.
Which is internal to the model. Yeah, exactly.
Can you get the name of the constraint from the QQ variable or
No,
no? Okay.
I don't think so.
Like if I forgot for some reason, I don't know, I forgot the name of the constraint. And I have the
So-
pointer to the constraint. No.
So this is,
I don't know if you want to do that, but
that's a good question. I'm not sure.
You can get the name, you
Well-
can get the string.
You can go internally and see which key of the dictionary. There's a dictionary inside that and look for that, but you usually know the names you have. There's another feature which you add string names to the constraints and variables. But that's a step further and we're not doing that today. That's useful for, you can, besides of having this let's say programmer names. It's just names that you want to write in an LP file or in a MathOpt format file. And those names you could query back from the names.
Can you ask dictionary?
What?
The dictionary that has the constraints?
Well, I can.
I think if you don't add additional code, there is no name stored somewhere because it's a symbol, right? I mean, you could say, I want to transform the symbol to string and store it, then of course you can access, but if you don't add any additional name, it's not stored, there is no string stored somewhere, right? Because once it's compiled, this is transformed into something not necessarily correct, right?
Oh,
When you run the code, it'll create a symbol called conref.
it creates an internal reference in the models.
No, yeah. So I guess like three ways of referring to a constraint. The string name, if you created a string name, the pointer, which was a verbal conref that points to the constraint, and then the symbol colon conref that you can recover by asking the model, give me back the pointer associated to this symbol.
Yes.
Can you ask about the give me back the pointer associated to this string?
I think so, but you had to create a string before.
Yeah, that's what I'm
Yeah.
saying. If you don't
Well, this is a symbol. If I use a string, I don't think it will work.
But if you created, if you also gave name the, how would you name a constraint with a string?
Oh, there's a function for that. I'm not sure if it exposed it. Set name?
Could you recover the, but the dictionary is indexed by the symbol, not by the string.
They're completely without
Yeah.
the symbols and the string.
Alright, is there a dictionary indexed by the string?
Yes.
Yeah, okay.
You can look up by the string.
So you could create half your constraint with the symbol, half your constraint with the string, and you can get some of them with the string and some of them with the symbol. And some of them might have both, might be indexed by both if you did both.
Okay.
So you can take whatever.
Joaquim, how can you look through the constraints?
What do you mean?
Iterate?
Iterate, like access every constraint of a single model.
Using MLI, you can rotate it.
Yeah, so that's an advanced operation, but that can, because now JuMP doesn't store the constraints. It only stores references to what's happening, and all the constraints are pushed to either a temporary module or straight to the solver. So you have to use MOI functions for that.
So if you iterate through either.
Another option is that every time you create a constraint, you can create a vector of references, and every time you create a constraint, you push that reference to your vector, and then you iterate through your vector.
But you can iterate over the dictionaries.
Yes.
But you have no guarantee that those are all the constraints. Because if you didn't
Yeah,
give it a symbol or a string, it will not be there, and that was your responsibility.
exactly. So, of course, you can get into the data which is inside your model, going through the hard way, and seeing what are the fields of the struct that holds data for the model. But that's not good practice. You should use the API functions for that.
So this your model column ref is, like you said, I'm pushing each constraint, but in some sense, like it's what it's doing is pushing that, but stated in a dictionary index by
Yes.
that symbol instead of the. Oh,
Yes.
And what if I create an array of constraints?
Yes, that's the next part. We're going to reach that.
But I was like, it's your responsibility to say your constraints. But then this actually makes your life easier because you just told it,
Yes.
save it with this name. Now you wouldn't lose it. Before you had the variable, and if you override the variable,
It
you
depends on if you're a solver, you need to access all the constraints.
right, but that's an MY thing. As the JuMP level, you should save your constraint somewhere. And again, this will save it indexed by the symbol or the string if you have the string. But if you want to push them to a vector, you can push them to a vector. Same as like I said, think of it as like a variable. You have a variable you use to save your variables. If you overwrite it, it's
So the next part is, okay, but suppose you have a large number of variables, and then something very common in linear programming is, well, you have a sum of many variables, and you don't want to write by hand this. I'm summing 1 to 1,000. I'm not writing 1,000 times that thing. So there is this sum construct where here we are creating a new variable w, a vector variable with indices w1 up to w4. And then we are creating that constraint over there. A times where, well, A is defined here to be a vector. And we're doing AI times WI for all the 4 entries of W to be smaller than 3. So this creates exactly that constraint over there with X replaced by W. So this is a very useful construct which you can use sums over here. You can do more also. Sometimes you want to have keys like conditions like this. So you could also create a constraint iterating here in a loop or adding a condition over here. And well, there are some details about how the reference, oh, not here. Okay, this is only this. Yes, this is the next part. So Juan Pablo was asking, well, sometimes you have multiple constraints with the same format. So yes, you have a family of constraints that depends on a vector or some index. So here I'm adding this constraint 6x plus 4y is larger or equal than 5 times I. And I'm doing that for I between 1 to 3. So this means I'm creating 3 constraints at the same time. And this will be the reference for all of them. So it will be a vector reference of constraint. It will be a vector of constraint references with some detail. Yeah, you can.
Might be next to the recursive.
So when you run, of course, you get, well, I had already 3, maybe 31. So, yes. So I'm adding a constraint, but actually it's a group of constraints with the same format. But, well, depending on your constants, you can or not have some variables in some of them or not.
Can you work the support function in that code?
Yeah, was last talk. You can get rid of it. So what happens here is that the return of this function are 3 references because we created 3 constraints. Please.
And what's the syntax for getting them back with the
Yes, let's go for it.
Actually, there are like 2 natural ones. I tried both of them. One fails, the other one doesn't. I had no idea. First time I seen this feature.
Oops.
No, you did.
Okay, yeah.
But maybe to your model.
Yeah, I'm doing that.
Can you indexing from your model?
Yes. So you only created one name here, which is conref31. So if you do the your model version,
Do the one that will fail first.
okay. The one that will fail is this one. Because actually something weird happens here, like this is not a symbol. If you wanted this to be a single symbol, you would need to have parentheses, but still this fails. It's actually an expression, right? So what you need to do here is you get the vector of reference. So this will return you the 3 elements because it's a vector of references. And if you only want the first one, then you do this.
Okay.
David?
Why the output looks like very scary? Like so many letters.
Because you shouldn't look at the output.
It's not right. The printing is not updated. That will not be the function.
Oh yeah, so in the past, we had a nice printing. I think Miles and Benoit are working on getting that back, where it prints like the constraint itself. Or maybe something prettier than that crazy. Yeah. Please.
Can you include conditions on the indices? For example,
Yes.
from Q?
So there could be any, so that was an array of 3 things. It could be any of the 3 containers. How many containers are there in JuMP? So remember there was like what were the arrays? The regular dictionary. This, what's the name of the other Julia array? The JuMP array? Which is sort of like this Cartesian product of dictionaries, or a regular array. And those can have, so for this Cartesian product of dictionaries, it could be any conditions, and it could be a completely abstract dictionary that is indexed by the arcs of your graphs. So this constraint could be, if it was 1, 2, 3, it could be really conref31, then you would get a dictionary that's indexed by edges, by nodes, by paths, by whatever.
I think that should be an if, maybe, instead of the comma. Will it work? Yeah, somebody tried. Nice. No, it's working. So if you want to use conditions for creating the constraints, you can do this way. So I want to iterate between the numbers between 4 and 12, but actually I just want the ones that are greater than 5, and I don't want 10. So it creates a dictionary of references with 7 entries, which are, okay, The dictionary doesn't have to be in order, so 4 is not here because it's larger or equal than 5. And 10 is not here because it's different to 10. Yes?
And then how do you access to one particular constraint?
Yes. If you want to access that again, then you go here. Well, 32. If you try to access 1, it will say, well, key 1 doesn't exist. If you try 4, it will say the same because you haven't created any reference for that. But if you say 5, it's there. But, well, I didn't want to print, but that it is.
Can you keys?
What?
Keys.
Yes.
To show the keys of. So keys of that will give you.
Oh yeah, you can do that also. So this returns a dictionary, which is said over there is a dictionary of constraints instead of a plain array of constraints. And if you want to iterate through these constraints, like, well, I don't remember which are the values, you could do keys. And so it returns for you all the keys. If you just want the references, you can do values. And it returns you all the references. So you can iterate in one of these two fashions.
You also do four constraint in your model conref blah blah, and this will be a for loop.
And I assume that something similar applies to variables, right?
Yes, exactly the same applies to variable. So you can use it's actually the same style of construct that you can use for variables. Okay? Well, and also you can have, instead of having numbers, you can have like anything else. Should it work? Why is it multiplying? Oh, okay.
Oh, sure.
Okay. So now, oh, now it's a jump array. Oh, it's written here. Now, instead of having a dictionary, we have a jump array. Okay. So, how do you access the indices of a jump array? Are there something to that? Well, you can query them back.
The name changed recently.
You can query them back like this. Or, well, if you have your set in hand, you can go through the indices of your set, through the elements of your set.
Why
Okay.
is it a jump array?
Because it's a continuous array that is referencing the reference. No, it's
No, it's a set.
no, it's a set. Yeah. Please, Gustavo.
So suppose that for some reason you have that set of constraints and the form of the constraint is different for odds and even.
Yes.
Can you have like a conref 33 indexed by 1 through 5 and another piece indexed by 2 and 4, or that's...
Well, you can. Yeah. Or you can be generic enough in the definition of the constraint. So there's actually a few things you can do, like, but then you can go crazy with stuff like, I think you can do I equals a, write this, otherwise write 0. I think you can do this. Let's see. Yeah, but that's Julia's syntax. I'm just saying, okay, so if I equals a, then right there 6 times x, otherwise just write 0. That's part of the advantage you gain by just being a programming language with a bunch of features. Well, the other way you could add those constraints of that kind, you could add them in a for loop. And then you can actually create a you can create a vector of references.
If you want a dictionary, you can ask for it.
So why did the I?
And then
Fits in the jump array.
you
Why this conditional it was like a 1 to 10 minus the 2 numbers? It kind of give a dictionary instead of a jump array.
If any conditions give you a dictionary, you don't have the ability to know if the conditions.
so you can add them in a loop, grab the references, and save them in a array, for instance, and then you can have an if inside the loop.
And in that case, you have a way to give them internal names.
That would be crazier. I never tried.
They don't have an internal name.
Yeah, they will be anonymous.
Those will be anonymous, but
Yes. I don't think you can like programmatically add some variable, some name that varies in a if loop, in a for loop.
To print the name of the variable, like there's the string that is the name of the variable, and then there's the jump or the Julia variable that points to the constraint. And then there's the symbol inside the model. So we don't have that.
Yeah.
I think that's the key to understand exactly what's going on. That there are these 3 things, which is actually 4. There's the object, which is the whatever contains the variable to constraint.
Yes.
Whatever Julia variable that's pointing to that object, which could be anything. You can say y equal red, and now y is equal to red. There's the symbol. If you created a symbol that is saved, that you can index by asking the model to give you back the object associated with this symbol or this string. And sometimes those are 3 things that are somewhat independent, depending if you create it or not. And if you think about it that way, you can immediately understand what's going on. So if you were to overwrite the Julia variable, of course that makes sense. If you were overwriting a variable. And I think now that's something that wasn't so clear before in the previous syntax when you created a variable that suddenly this x was the same x as was a string, there was a symbol, and there was the variable, and this is like, what's going on? No, all these things are different, and you can decide to use one or the other.
Okay.
Any performance difference in the performance using the loop or the other one?
Yeah, there shouldn't be much of a performance. Well, depending on what you do, there might be like some ridiculously small penalty from using arrays and dictionaries. So if you're having an if condition inside of creating a constraint, and that's a lot of constraints, you can just create the ones you want with an if, and then push to save the references to your array, and then you iterate in it. But
When you create a block of constraints, it's exactly as if you wrote the loop yourself.
Ah, okay.
yes,
Okay.
but then accessing it back would be the only difference. But creating the thing is the same thing. Yes.
I mean, whatever you indexed from, that might cause trouble.
Well, there is a
Like going over the index, so it will be the same for
there is one.
It's a bad case if you're
Yes. Let's see.
you have a graph, you're looping over it, 1 to n, like for I and 1 to n, j and 1 to n, and then check if the edge exists. That's a quadratic operation. So you should write as you loop through the edges.
Yes.
So
So
it's like that if you write down that shorthand on the constraint, it will be the same as writing down the wrong loop.
so here,
Your loop is bad.
That's
Your
what
loop
you
is bad.
have.
It's not about.
Yeah, sure.
if you do here, I in 1 to 4, and then j in 1 to 6, and then a condition I.
Equals J.
No, that's the case that it doesn't make a difference. But if you want to check a condition on I, then this is the case it makes a difference.
But I guess if you see that, you can read the for loop.
Yeah,
Doing
exactly.
For I, 1,
So
1 to 4,
the
J,
thing
1
here
to 6.
is that this creates nested loops, but if you're only checking conditions on the very first loop and you have a bunch of other new loops, then this make a difference. You should write the loops separately, so then you can check, because this way the condition is only checked in the innermost loop. Exactly, so you're doing a bunch of useless iterations. So if it's like a very high performance thing, you might pay a penalty for
Could
that.
that be I greater than J before, so I
No,
greater
you
than
can't.
before the J? So
So,
there
yeah.
you have to write explicitly.
Yes, so that's a recommendation on the JuMP manual, I think. It used to be.
But I feel like if you read that the loop will be exactly the one you read there, and if that's slow, the loop will be slow. So
Yes,
it will not be slower than the loop that you can read from the index condition.
yes. And finally, oh, okay. Going back to constraints.
So yeah, it used to be possible that you could create a set of tuples. And
Yes,
somehow when you,
you can do
when
that.
you index the constraints on them, they get yeah. It's still the case? Okay.
In what?
You can create the indices beforehand. So if you want to have like 2 indices, you can create an array of tuples like this.
Well, it gets splattered automatically.
Yeah, and I never gotten why it's actually I like that it's not a tuple that I get, but I never understood why. Because it feels like a violation when you get when you define a set of tuples and then you index on that set and the index is not a tuple. It's not, but it's plus.
This is the most common error. So then you want to access this guy at, if you do this, this works, but I think you can also do, no, you cannot. So it used to work, but I don't know.
With Julia Dictionary, so that's a special.
Okay.
Well, then, if you want to see it as an array with two
Yes.
dimensions, you can access 1, 2 in square bracket.
Can you? I don't think so. I think you have to use 3 dots. So if you have an array, I think that's what Francois is asking. So if you have an identity matrix.
Say you have a very sparse matrix and you generate the sets of non-zero value to start with, and then you want to access only the thing.
So Julia has a sparse matrix structure. It creates a sparse matrix with only the indices you need. And then if you want to access some index, oh, wait.
Because in this situation, saying you have a very large network and transition ij exists only on certain conditions, and you don't want to bother about resetting the condition all the time, so you generate a set of possible conditions to start with.
And it will be a dictionary.
Yeah. Exactly. Or you can use a sparse matrix and ask for its indices. Well, you can create a sparse matrix from scratch and then use that as an iterator.
Because you would like to access it from node I to node j, say whether the variable exists or not.
Yeah, it's easier to make a dictionary.
You can ask the dictionary, is this a key? Or you can iterate over the keys. But you can also like, is this one of the keys? And it will say no. And if you checked it before accessing, actually, is it throw an exception to? Could you can't? It's better to check if the key is here. Actually, what's a sparse matrix? Today do a sparse matrix of what is that? So sparse matrix CSC of JuMP var, N64.
Yeah, you can make it.
What we have in our modeling language is that people who generate the variable instance to start with, and then when they loop over them, when they access one that does not exist using the two indices like a table, it will just do nothing. So then they can be unclean.
Hacky, yeah.
An access key that doesn't exist today.
You can do one with it now.
Well, right now you get there.
Yeah, we currently have an error.
You could write one line that says, is the key there? Question mark, then access it.
Otherwise, 0.
So there's a way to.
No, you can send 0, so you can sum that easily.
There's no, it doesn't make, there's not a default value that always makes sense. Like if it's a dictionary of constraint references, what do you do? What do you return 0? Like nothing. Well, nothing. You have to return.
So I guess it's like now there's this new the nulls or the nulls. What's the word called?
Yes.
So like if you have data, you can have numbers and then nulls. And there's a way of actually doing it very complete, but it's for numbers and nulls. So you could potentially do the same thing and have, and as long as you know what the behavior for that null is when you do something with the constraint, you could, if you can implement this and create an array that has nulls, and then if your function, if you override the functions for whatever it is that you're doing with the constraint, you can make it so that when it looks at null, it doesn't do anything. And that might be, maybe it might, I don't know how much faster it would be than the question mark. I mean, I don't know how they make nulls fast. There's a whole point of making nulls faster when you have numbers, so that it wouldn't be ambiguous.
Okay, was there another question? So we can go to objective, which is basically almost the same as constraint. You add an objective to your model, you add a optimization sign, either a min or a max, and then you can add your objective, typically a linear objective summing, well, coefficients and variables for some array. Okay?
I guess
Some question?
yeah, one about so I guess it's like these simple ways of creating, so if you do the one with the brackets inside the constraint and variable, you can create one of these three objects that you have.
Oh yeah.
But if you would like to index your variables and put them inside the weirder container, you could write down the for loop and fill the container with the variables.
Which is what is done over here, yeah.
Yeah.
So I just chose to use an array and I'm adding stuff to an array, but you could use any other kind of data format. You want to use a linked list or anything else, you can just go and do
I
it.
guess you could create so like that constraint doesn't have the symbol.
Yes,
So
it's an anonymous.
Something it doesn't have. Can you programmatically create the symbol?
No, that was the question. Yeah, can you? And can you add that as a name?
Yeah, if you go model square brackets, might call new constraint.
You can
Square
assign
brackets equals something.
Yeah, you can assign by brute force, but
You can do this.
can you put something here like,
No, not there. You go. You go like this.
okay, your model, okay, got it.
There you go.
Your model, 2
And
points,
then you have to go like simple.
yes.
And whatever's inside the symbol could be an extremely weird string construction.
And then you can go.
Yeah, I don't think
And you do whatever you want.
everything can go. Any string can go inside symbol right now?
Oh, that's
I think like if you use Unicode symbols, it can't, but
But it could be a very, very complicated
Yes.
construction of the. Could
Yes,
be,
exactly.
Arc of
yes.
like your value.
Yeah, it could be
weird
something
and
like-
things like that if you want. But it won't be an array of. You won't get an array or a jump array or a dictionary. You'll have this single way of indexing it with symbol, whatever it is. Yeah,
Yeah.
exactly.
And you can interpolate numbers inside of it.
And the loop could be as crazy as you want. It could be nested. You can do it.
So since we are playing around, maybe too much? Oh, okay. Parentheses. Yes. But you can have the weirdest thing as you. So yeah, those were objective also, pretty easier, simpler.
So
And
you can always fall back to doing crazy Julia things if you want.
Okay. So now let's solve another optimization program. What, Oscar?
Now we get to solve something.
Yes. We already solved something.
Okay.
One thing.
What happened with the objective?
Well, the objective is just like
Ah,
a little bit. You have like a linear expression, just like you had for constraints, and you can have either max or min, just saying either you're minimizing or maximizing. Yeah, it's nothing very funny about that.
if you run an objective twice, it overwrites the last objective.
Exactly. So there's another notebook for that. I actually don't even know what time is it. Okay. So we can solve something, and this is like a generic form of an optimization program, which is not the cleverest thing to do in Julia. You don't want to give to JuMP matrices A, B, and C, because, well, you can just, you can, but it's better to write just in a sparse form. Well, this problem is basically dense, so you can prepare everything beforehand.
Unless you're reducing it.
Yes. So first I create a model, I add an optimizer to that, and then I create some input data, the C vector, A matrix, B vector, and I just say the sizes because they're useful for creating variables. Now I can create my variable x, which is indexed between 1 to n. All of them are positive, so I have 4 variables over here. And then I can add my constraints. So I'm adding m constraints in a for loop, but I could add with a name over there. And I'm summing all the indices for all the indices and saying that's equal to b. Then the next step is to add an objective, which is a minimization objective. I add a linear function based on this sum. Then I can print something, which is not working, but it will be back soon. And then, like we saw before, we can solve the model. So we use this optimize function, and then we check, okay, so was the model successfully solved? Do we have a feasible primal solution? So on and so forth. Then you can print some results. And here is the whole code again. So the model, the variables, add constraint, add the objective, solve the problem. I'm timing the solution time. Query if the problem was successfully solved, see feasible points, and query solutions. Well, here I'm querying the objective function and the result for the variable x, and I'm printing that. So the objective function is 4.92 whatever, and the optimal solution is this vector over here. Note something. If you use result value without this dot, this will fail, because result value applies to a scalar object. So we use the dot object to say we are broadcasting, which is we are vectorizing that function call. So we're saying take this function that receives a scalar object and apply it to this entire vector, which could also be a dictionary. So it just goes through all the indices and solves and evaluates the function for all the indices. It's like a for loop instead of explicit for loop.
The model does not appear on this. How does it find the model?
The variables have a reference point.
Yes.
So I cannot have two models with two variables named the same.
Yes.
I cannot do that.
Yes.
You can.
You can. Because, again, it's the same thing. You have the references on your scope, so you can create an x variable, but then you rename, then you say y equals to x, and you hold that value on y, and then you create another variable for another model named x, and that will be your x. So you have two different variables, which inside their models, they have the same name, but outside, they have different names, just because you want to hold that. There's a little bit about modes, but I'm going through that later. But so if you want to look later about modes, there are examples using all the modes of using JuMP, like direct mode, automated mode, and manual mode. They're all in this notebook. There are a few slight differences between each other. And then, well, I'm going very rapidly through this MIP problem. So, just like the same for what we did in linear optimization, now for integer programming. So we have all this data, we're writing the program in this generic form, C transpose X plus D transpose I, where X is a real and Y is an integer. And we have those constraints and positiveness for the variables. So this is the data for the problem. I just picked random numbers. And then you create a model. Now I created an empty model. My bad, I should have done this other way of using JuMP, but well, let's go. I added a variable, I added the X variable, which is continuous because I'm not saying anything. I added the Y variable, which is integer because I'm saying int. Then I'm adding a minimization objective and then a bunch of constraints, which have like two main pieces. The sum of the the variables with constants in the A matrix and the variables with constant coefficients in B matrix in the right-hand side. And then, well, since I haven't said which solver I'm using, I'm having to add a solver, which I'm doing this 4 lines here. We can go through that later. So I create a solver, I kind of say to the model, well, this is the solver you're gonna use, and then this step just passes all the data to the solver and then solves the problem. Well, if I had said before which solver I was using, then this would be seamless. I wouldn't have to use the first 3 functions. I could just go straight to optimize. Then I query some statuses and print some results. So a JuMP model, termination status is success, a primal status is feasible point with this solution and these variable solutions. Okay? There's a reference from an old paper from Miles and Ian. I think they published that? There's a published version, right?
No.
In the Informs?
Ah, yeah.
Okay.
Here.
To appear, yeah.
Is it 20 working?
So now we have a few options. We can look at a example with a graph.
I think the
Which one?
detection solver.
Do you want to do that?
Let's cover more breadth.
Yeah. Yeah, I agree. So the options are, well, I'll mark them. Is a small problem about Chebyshev center. This problem has a graph. This is a nonlinear problem. The Sudoku is funny. And we also have Bender's decomposition. This is what we did. And there's a little bit about exploiting sparsity. So those are the ones that are working for today. Anyone has a preference? So the graph. Yes, this is the one. No, it's not. Actually, it's not a graph. My bad. I thought it would be. Let's see. Yeah. Let's see if the other one has it. I think this is also a complete one. Yeah, this is a graph. Okay, so let me focus a little bit. So the notebook we're going into now is this Shuvmoy exploiting sparsity. Again, we're using GLPK, and then what? Miles probably knows.
He was a master student in Toronto.
And now
He worked with the railway.
okay. But he's still working?
I think so.
So yeah, this is a transportation problem, and there will be a few steps over there. A problem setup, we just create data and load data for the problem, and then minimize the shipment cost over relevant routes around the world. There will be decision variables and constraints. So the cities which will be connected will be these: Bangkok, London, Paris, all of those up to Barcelona. And there will be products, I think, being transported from one place to the other. In this notebook, it's nice because it teaches you a little bit about Julia, some interesting structs that you could use to model your problem easily, just to manage data, basically, because the JuMP constructs will be basically the same that we saw before. So they create a type, which is a struct holding three things. A product being transported, the origin and the destination. So there's an example over here: a route carrying a smartphone from Bangkok to Singapore, and here from Bangkok to New York, and so on and so forth. This creates routes, and then this is just showing that, you have an array of routes, which are each one of those. Something else you could do is that you could create this other struct, just saying the product name and the city where it's created. And then you have a list of all the supply cities. So this is basically creating the nodes. Then it's showing how to use a dictionary to hold the data. So you could have a dictionary of those problems. You could store cost coefficients in these vectors. What else? Okay, and then he builds a dictionary attaching to each route that they're using a different cost. So it's basically costs on edges of a graph. So the cost of transporting a smartphone from Bangkok to New York is 205, and all these values over here. So he writes a mathematical program with all that. So first defining the graph, we have the set of cities will be the nodes, the set of products, which will be like the things getting inside the nodes and outside the nodes and being moved through the edges of the graph. And also R, which is the cost of the edges, because it knows, it's the edges, because it knows which product is being transported from which city to which city. So it will have 3 overlapping graphs, because we'll have 3 products, I think laptops, smartphones, and something else. So this will be the model. So this first constraint here just says that the amount of product getting into. Some cities are fixed, is the supply. There's also a fixed demand on each of the nodes, which could be of different products for each one. And there's also a bound on how many products can you move from one place to another. And now just mapping this constants to, well, the names of the variables in the code. So C for cities, P for products, R for routes, O for origin, D for destiny, S supply, D demand, X the transported amount, and C costs from routes, and gamma the capacity of each edge of the graph. So the limit of what can go through the node, through that thing. So there's a data file for that. So instead of like reading a raw data file, we just defined the data in this structs over here. So a vector with cities, a vector with products. So this is enumerating the nodes. This is enumerating the 3 overlapping graphs. So there are edges for each of the graphs. So the routes are smartphone routes, and well, from Bangkok, Singapore, Bangkok, New York, so on and so forth. There are tablet routes, and there are laptop routes. There's also the supply data. So here we are fixing values for supply. So we're saying that, well, we're just creating a dictionary on the run. So if the supply origin is if the product is a smartphone and the origin is London, then the supply amount is 800. And well, we do the same for all the other cities and all the other products. There's also the customers, which are the demands of the products. So the demands of smartphones in Singapore will be of 400. Singapore wants to 400 smartphones to be there in their node, and so on for the other nodes. Here are the costs of all the edges, and now just creating a dictionary from edges to costs. There is this other loop that is just saying the amount of product input in the nodes. The same thing for demands. And then we can start to write our optimization program. So the first thing, if you want to do a JuMP model, you have to start loading the libraries which you're going to use, which are basically JuMP and GLPK. These are the ones I don't think they would be necessary. They would be if we were using some special mode in JuMP. But then we start creating, well, we will build the same model that is written in LaTeX over here. Which, how do we do that? Well, it's pretty similar to what is written in LaTeX. We create a variable, which is the X variable on that model, which is what we are transporting and through each route. So if you remember, routes is it's a dictionary of routes. So it will create a variable for each of these routes, which represent the edges. So it will represent how many products are going through that route. So how many smartphones are going from Bangkok to Singapore. And okay, so this creates the routes. Yep.
I know it doesn't apply here, but how do you declare a free variable?
You just do this.
Okay,
this would create a free variable. And then you have an objective. You want to minimize the cost of transporting everything you need throughout the routes and demands and supplies. So you're minimizing the sum of the coefficient costs for the edges through all the edges. Then you have the first constraint, which is, well, the supplied amount must leave in the correct amount. So we have all this supply in this node, so all these products coming into this node, and this should match everything that leaves the node, which is the graph structure. We have an outer loop for products because, well, we have 3 overlapping graphs, each one for one product, and we want that all of the separate graphs are feasible. There's a second constraint just saying that demand must be met in each of the nodes. So products coming into the nodes should sum what the node has to leave, has to take away from the graph. And finally, the constraint that says, well, this edge links this node to this other node. So this is the interesting constraint because, well, you have a for loop on cities, 2 for loops on cities because, well, you want to see which nodes match which nodes. Well, you just check if origin is different from destination. Otherwise, well, that supply could be met by the nodes on production. And now you're summing all the routes, so all the edges that has as origin the node RO and as destiny the node RD. And this edge should be smaller. The sum of these edges should be smaller than the capacity of the edge. Okay. So the 3 graphs are overlapping, but they have the same bounds. So probably the story the guy is telling us is that they have the same trucks to transport smartphones, laptops, and notebooks. So we are summing all the edges of different products going from one place to the other. And then we optimize the model, and then we can see the results for that. So we get the objective value, and then we query the result value for each function with this dot operator over here. Because remember, the result value function only works for scalar objects. So if you have a container that holds many scalar objects, you have to broadcast through this container, and you use the dot operator for that. Just like vectorization in R or MATLAB. And here's the solutions. That's what you get. This is probably the most complicated of these notebooks because it's a graph example. And, well, that's it. It's easy to model that with JuMP. You're basically just writing whatever was written in the LaTeX format before. So
Joaquim?
Yep, please.
So I guess Gustavo was mentioning this. Can we talk about like referencing variables for a bit?
Yes.
It's a user case. So I have the following
Yep.
situation. I have a function that receives a model
Okay.
and a subset of variables from that model. Right? So, I mean, so like an array of variables or something like that. So how
Okay.
can I reference those variables if I want to add a constraint, for example, using those variables in that model? I don't know if I was clear.
Yes. So
my function doesn't know the
indexes.
In that model. I just know I just get an m and a vector of variables.
So you have a first function that creates a model.
So how do you know what the structure of the variables getting passed in is if you don't know what they're? Well, you know you always get passed in 3 variables, but you don't know.
No, for example, let's say that my function does the following. They give me the model, they give me a set of variables, and they give me a set of values. And I fix those variables to those values. I have to add those constraints in the model. But it could be any model, I don't know.
Do you get a vector of variables and a vector of values? Or like how
Yes, but but I would love to use, of course they could give me like a vector of indices for variables, but I want to make it like general. Like I don't have to know the indexation of the variables. They can give me the actual variable objects or copies of them, and I can just say.
So that works.
Because I read that you can actually, for example, if I'm also the user that is calling this function, I can just use the add variable function, and I will get a copy. If the variable already exists, I get a copy of the variable or a reference to the variable. No.
So there are a few options. What I think you're asking is that, well, I created a model and a bunch of variables somewhere else, and so I have a model here and some variables here, and then I want to add constraints to that model.
Over a subset of those variables, for example.
Yeah, so you have to know which are the ones you're accessing. So you have 2 possible options. Either you have stored the reference for your variables. So
no, I mean because the user.
Yes.
So there's the user that created the model and the variables and everything, and there's me, which I have a function which the user is gonna call. Okay. So the user knows the reference to the like how he indexed or she indexed the variables, whatever. But then he's gonna hand me the model and a subset of variables.
Okay.
So how?
But you know the semantics on how those variables are organized, for instance. What?
I'm asking if you can not know.
Well, but then how would you know what to do with them?
We have an agreement with the user that.
Yeah, so you know the semantics.
My function does what I described. You give me a model, you give me a set of variables, an array of variables, whatever.
And you sum all of them.
An array of values, and I just, and I fix, and I add constraints which are fix these variables to these values.
Okay, your function. So your function receives a model, some variables, and some coefficients, right?
Yes.
And then you want to add constraints for each of the variables. Well, I'm supposing it's array, but we could use each index. We could go through all the indices of the variables, and then you can add a constraint given that model, and you say that that variable equals those coefficients. And
yes, and we're assuming that bars is an array of variables.
Yes. Actually, I'm not even assuming it's an array, but
yeah, I know what you mean. Yes.
Yeah.
But the add constraint is going to understand that.
Yes.
Okay.
So this is getting back to the difference between so bars there is the Julia object that points to the variable. It's not the, so there's the
it's
bars,
not, yeah.
There's also X, which is the symbol stored in the model.
You could actually
so you don't have to write add constraint M and then X equals the thing.
You could test this if they are the same.
Yeah, so this is in the create function, we had the x, which made the Julia variable x. It stored pointed to that in the symbol x. So in the your function, we just need the pointer, not the x.
So nice. Yeah, okay.
It's like a little bit difficult to explain.
Yeah. So that assert line is
It's saying
what
that,
it's saying,
that the pointer, like
pointer.
m of x, is
Yeah.
pointing to the same thing as bars, which is a variable in
Okay, so x is just one variable. Okay. Yeah. So I'm just checking. Okay, is x exactly the same thing you passed there? But
Thank you. It's kind of like, I know there's a lot of assumptions that you have to make if you make that function, but yeah, I was wondering if you could do that without having to know that A,
yes.
the function, the variables are 1 to n or something like that.
Oh,
That's exactly what I was.
Nice.
Thanks.
In-
10 more minutes. Do we want to do another one?
what do you, so your question, you want to know if you, what?
Non-linear?
Yeah, so non-linear.
What?
I didn't understand your question.
Well,
Your question?
can we have your examples ready?
What? The question I just asked?
We can do fastly, nonlinear, and then polynomial.
Sorry, yeah, okay. Ah,
Okay, so let's go through two different examples. The first one is nonlinear, and then we'll have a polynomial optimization example with Benoit. So there's this old notebook by Ian, which does rocket control with JuMP. Pretty exciting. So there are a bunch of equations describing the nonlinear dynamics of how the rocket should work. So there is velocity as a derivative of distance, acceleration, mass loss because of the fuel being used by the rocket, and there is this, well, drag, which is just like, yeah, the rocket being deaccelerated by air, whatever is out there in space. So this example uses JuMP with IPOpt, the nonlinear solver. And we start just by creating a model just like we did before, but now we're using IPOpt optimizer, which is exported by the package. We're asking, hey, IPOpt, would you print some stuff so that I can see what's happening? And then we create the data necessary for the problem, like initial rate, initial velocity, like initial conditions are here. We create a few parameters, speed, some stuff like that. And then we derive the correct parameters that we need to the model. And now what we do is that we create the variables. One of the variables is actually the time step. So it's optimizing also the discretization of the model. So how much time would you stay in each step of the solution? Then you have the velocity vector. So for each time step, you have a speed. For each time speed, you have a height. And for each time speed, you have a mass, which has to be between these two bounds. And the control. So how much are you using your acceleration, your thrust? So you can create a bunch of variables in the same block instead of going through add variable, then add variable again, and so on and so forth. But all of them are being tied to this model. Some of them have bounds, only lower bound, and some of them are inside an interval.
so each new line is a call to variable. Or no?
Yeah, it's like that.
Kind of.
It's like of each of these line, you could, instead of write a block, you could write add variable for each of those. And then we have an objective, which is, well, we're going to go as far as possible. We're summing the height at the last moment, h of n. And we have now more constraints. The constraints, these are linear constraints. So constraints is basically always some linear or quadratic expression inside a set. And if you have some nonlinear stuff, then you have to use the nonlinear expression and nonlinear constraint things. So this creates the initial conditions, which could be, the initial conditions, which could be bounds on these variables if you create them separately from the others. There's this interesting feature of JuMP is that you can create expressions instead of creating the constraints straight ahead. So you kind of create just the right-hand side of the constraint, or just like two right-hand sides, and you're summing both of them in a forthcoming constraint. So here we are creating expressions for drag. So it's an expression, it's tied to this model, it has this name, it's being created for j between 1 to n, and this is the expression. It depends on these two variables, and it's nonlinear because it has an asp, it has a quadratic thing, it has this multiplication and divisions, which could be linear. We have this other expression, which is gravity, and this expression, which isn't even nonlinear, but doesn't matter. Well, it's just a constant times some variable. And then what you do is that you write the dynamics for all the time steps. Well, 1 is fixed, so you write from 2 to n, which is the last step on your discretization. And then you add nonlinear constraints here. So the height should be equal to the last height plus this, which is actually a linear constraint. And then you have these other two constraints for the integration of the drag. So you're integrating using some trapezoidal rule, and the drag shows up here, as you can see. This was never a variable on your model, so we don't have a variable for drag, but we have an expression representing the drag. So wherever we see drag in the future, JuMP will replace by this expression over here. So instead of creating this expression, I could just grab this expression here and paste where is drag written over here. Okay. And then there's this trapezoidal integration about mass, which is the difference of mass. Then you could possibly provide an initial solution, and what you do is, just like the linear models, you go on and optimize the model, and you can query for objective value, which is over here. The furthest you went is like 1 point something, just scale for that. And the use of getFly is basically to show this nice plots over here, where you can see how all the variables behave throughout all the time steps. So here is showing the height, it's reaching the mass, what's happening to the mass. So it's probably used all its thrust up to here. So yeah, that's what happened. It started using the thrust, it reduced it, it started to grow back again, and then it stopped. Probably because of lack of fuel, something like that. And this is what happens to speed. It starts to grow, and then it just moves until the drag stops the rocket. And so here speed is back to 0. And all of these are queried with JuMP results. So exactly the same as we did before. So nonlinear models have the same infrastructure. They basically, the biggest difference is that you have nonlinear constraints, then you have to use this @nonL NL constraint macro. Please.
Can you comment on the viable creation? The Delta T1 has,
Here?
yes, the start is something I didn't see before.
Oh, okay. This is initial value.
Yeah, that just provides, it's a short way to provide the starting point to the software.
Okay, so it's only for IP or it's for organism?
For all software.
If you provide a partial start
But-
with some variables,
Is that just for?
That if you don't provide a, okay, yeah. So that also depends on whether your solver can use this information or not. So you have to know if your solver is going to use this information.
I think that start is provided because if you start at delta t at 0, it's
For all the things,
bad
it's
point.
because you're figuring out the discretization. So if you start everybody at 0, it's a little weird.
So the parenthesis is compulsory?
This is what?
I'm wondering about the syntax of this thing. How does it look like with just one variable without the block?
You don't usually have parentheses there.
Here, right? You could do this.
Yeah. I think that's a quirk of how Julia parses those blocks.
Chris.
so you had some of the constraints were actually linear, but you provided them with that ML constraint. Is there a penalty potentially to that?
That depends on the solver.
But
Oh, well.
it's faster for the AD if they come in as linear constraints.
Right. So that probably should be there.
Yes.
Okay. So also, and this is a question better offline, but like, does JuMP really need to have NL constraint different from constraint?
Good question. I don't know.
We've had this discussion for a long time.
Yeah. All right. Well, let's talk offline. Yeah.
It requires rewriting a lot of things.
Has it happened? Has the discussion happened since MathOptInterface?
What was the question?
MathOptInterface is mostly open.
Okay. Whether we really should.
Is it macros or constraint?
For one for the linear, one for the
Yeah, so actually, even that the question is like, if somebody asked a question about what if I want to do exponential of sum of a matrix times x variable vector, and that won't work on because the AD cannot go in the linear algebra. So what you do is create an auxiliary variable y, let's say, and do add constraint y equal a times x, a matrix y vector variables,
Benoit.
and then do
Benoit.
exponential of y with the NL constraint.
Yeah.
Like the trick now, but basically it requires redoing the.
Right. I'm
Yeah,
saying
the-
maybe there should be a need for trick, but it's no discussion for this. Kind of
No, but that's a big discussion. That's
Yeah, I
the big
think so.
discussion. The redesign of the NL constraints.
Oh, we should
it's
use
a
yours.
big question, and it's sometimes instead of just fixing the AD, maybe
Oh, we have a
well, should it just be f of x is greater than 0, or what else?
Don't you have HTML?
Should that have to be
yes, yeah.
convex? Whether that's a big question. So I guess it's like, and we're waiting for Jared, so maybe stuff too. Technically, it should be workable by Julia 1.0. So I guess that probably should be the discussion for next year. Because by the end of the year, hopefully we'll have AD and we can start playing and doing crazy things. So at least
Use
let's say
this.
by next year, it would make sense to have at least, let's say, still keep NL sort of like separated, but have at least linear algebra AD or something. Acting really basic thing.
Hey, thank you, Joaquim.
Oh, you're welcome.
Thank you. Very rude.
Now we have
I'm gonna steal all the
Benoit.
things for the.
Is it on? Yeah.
next year we do Julia Con first and then JuMP-dev.
It's getting competitive to get to Charles and the Julia card. I think this is
Yes.
this is the last year we get in, or at least I get in.
Benoit, could you zoom a bit, please?
Yeah. Like that.
Will this work on 1.0? Oh, sorry, in 0.7? By JuMP-dev.
Yeah, by JuMP-dev, yes. So, because currently JuMP doesn't work on 0.7, so.
Okay. But there's not like polynomial. You said you mentioned Hydra was.
Yeah, also because of JuMP partially. But all the polynomial package they work on 0.7. Yeah.
So it's all JuMP. With JuMP works. This.
Yeah. Enough. So for this to work, you actually need to check out sum of square and polyjump because they depend on JuMP. I cannot release them before JuMP 0.19 is released, of course. And of course, if you have checked out package, you know that you can always free them like that to go back to a tagged release. So in this,
I did not know that.
yeah, or you can just do git checkout. So what this notebook does is show you how to do polynomial optimization. So the objective is to actually minimize this polynomial under some semi-algebraic sets. So we want to be in this set, x larger than 0, y larger than 0, and x, y larger than 1. And we want to minimize this polynomial over this set. So as a spoiler, we can check, in fact, what's the optimal, why am I here? What's the optimal solution immediately? In fact, if you evaluate at these different points, you see that you have 1, 0, and 0, 1, for which the optimal value, for which the value is 0, and this value for which the value is 1 over 4. So if you use IP-opt, in fact, it would find this value, which is not optimal. And when we see that using sum of square, we find these two optimal minimizers. Okay, so you could use IP-opt to do this optimization. I think Joaquim has already covered that. And you could also use it, do it with IP-opt using the polynomial just defined by registering this function that takes two JuMP variables and evaluates the polynomial at these JuMP variables. So if you want to use sum of square, you need first an SDP solver. So you can either use, for example, CSDP or MathOptInterface MOSEC, which is the package to use MOSEC, because in MOSEC you only have the API to the Julia API for MOSEC, but you don't have the interface for MathOptInterface. If you want to use MOSEC with MathOptInterface, you need to use this package at the moment. But we do it with CSDP because maybe you don't have a MOSEC license. Okay, so what's important to distinguish when you're using sum of square is the distinction between JuMP variables and polynomial variables. Here we have defined two polynomial variables, x and y, here. And these are not JuMP variables. We're not trying to find, at least here, we're trying to find x and y values, but when you formulate this using sum of square programming, you're trying to say that some polynomial has sum of square for every x, y. And so x, y, you're not trying to find them, you just, it's just that when you constrain a polynomial to be positive, it will be for all these two x, y's. Why here, when I create a variable alpha, here I want to minimize this value of alpha, maximize it. Yeah, because here alpha is a JuMP variable, so we will try to find a value for this variable. And so we're trying to find the minimum of the function, so we will say what is the maximum value of alpha such that the polynomial is larger than alpha for every xy in the domain S that I have defined. So the domain S was x larger than 0, y larger than 0, and x plus y larger than 1. Okay? And if we find an alpha such that this constraint is satisfied, it means that alpha is a lower bound for the minimum of P on this domain. Yeah?
What happened to the comments, parentheses? Is that syntax
Sorry, maybe we're gonna.
The parentheses and the macros?
Oh yeah, they're optional for.
Yeah, it's
all
optional.
JUMP macros.
Mm-hmm. It's not specific to JUMP. When you do macro, you don't need to put commas.
Sorry about that. We're ignorant.
No, I mean, it's okay. It depends on the mood.
And actually, I have another rookie question.
Yeah.
What about the arrow? So if you go up, sorry, you go up.
Yeah.
Or down? Or,
Where?
no, down. You have like a point.
It was up.
Up.
Yeah, in the
Yeah, like a line 7 there.
Yeah. Yeah, I see. But that's this syntax.
Yes.
Okay, that was syntax imagined by Robin Dates for evaluating polynomials. So when you have a polynomial p, and you have here polynomial variables and here values that you want to assign. This should be a b, in fact.
Anyway, it's just
yeah. Anyway, so you, yeah, this is for this has nothing to do with JUMP. Yeah. Okay. So now, yeah. So we want to find the maximum lower bound for this polynomial, and this would give me a proof that the maximum alpha I get is at least the best lower bound I can get with this sum of square program. So if you execute that, you find that the maximum value is -2 to the power of -10. So it seems like the optimal value is 0, but it's maybe not the case. In fact, you just have an hierarchy of program to solve with higher and higher degree of polynomials, and you're not sure that for the lowest degree you actually get the best lower bound you can have. Because some polynomials are not sum of squares, but checking if a polynomial is positive, it's very difficult. But checking if a polynomial is sum of square, you can do that with semi-definite programming. So here, we're not really checking whether p minus alpha is positive for every point in S. We're just checking if it's a sum of squares. So it's sufficient, but not necessary. So in fact, if we didn't know that 1, 0, and 0, 1 had this optimal value of 0, we wouldn't know if we are done or not, if it's 0 or if it's higher. At least it's not lower than 0. But what we could do is, in fact, getting the dual of these variables. And it turns out that if the dual of these variables, which is a sort of measure described by moments, is an atomic measure, then that means that this value is the exact minimum, and from the atom of the measure, you actually get the minimizers. So here, for example, we get the dual of the variable C3, and then we construct a matrix of moment from the measure, and then we try to extract atoms to see if it's an atomic measure. And here it returns a new label with nothing inside. It returns a new label because sometimes it returns something, sometimes it does not. And so here it doesn't find atom because the measure is not atomic. But the idea is, as I said, you can actually increase the degrees. The reason is that to check that the polynomial p minus alpha is positive is a sum of square on the set, the domain that I showed, where x should be larger than 0, y larger than 0, and x plus y larger than 1. You could say that this is the case if p minus alpha is a sum of square plus a sum of squares times x plus a sum of squares times y plus a sum of squares times x plus y minus 1. The reason is in the set for which this, and this is positive, you will have a sum of square plus a positive coefficient times sum of square plus positive coefficient times sum of square plus positive coefficient times sum of square. So it's clearly positive for every point in the set. But the thing is, you don't really know what are the degrees you should set for these three polynomials. So in the example above, we have set degree 2 for these sum of square polynomials. But if we allow degree 4, so that's the total degree degree 4 plus the degree of x, y, and this one would be 5, 4 plus 1. Then, in fact, we get the same lower bound. So it's still 0. But now, if we try to extract the moments, we get 0, 1, and 1, 0. And the weights do not really matter. So it gives us, in fact, the two minimizer, 1, 0, and 0, 1. And so we know that these two achieve the value 0, the objective value 0, and we have a proof that we cannot do better than the value 0. So we know that the optimal objective value is 0, and these are the two minimizer. Okay. And to go a little bit into the details of what's happening here, the thing is, from the matrix of moments, you can build a system of equation, and when you solve it, you get the atoms. And so for the first program where we didn't have any atom, the reason was that the system that we had to solve is just x plus y equals 1. And this has an infinite number of solutions, so we cannot get the atoms. We need to have a system with finitely many solutions. But then, if we use higher degree, then we get a larger system, this one. And if you try to solve this system by, for example, getting Grosvenor basis first, you get this one. And then you can clearly see that this system has two solutions, which is here you see y equals 0 or 1, and then here you get x equals 1 or 0, depending on y. So that's it.